All right, well, thank you for coming. This is the, let's see now, fifth seminar in the ALE, or Apprentice Linux Engineer set of seminars that we're doing. This morning we did LXD. Of course, this talk, I'm sure as you're all aware, is about Docker. We will be doing our last seminar today on Kubernetes later on, so we won't be covering that now. And then tomorrow morning we're going to be doing software-defined networking, and then in the afternoon for the last session, Cloud Foundry. All right, so that's what we're going to do. Phil Estes is actually a Docker captain and does these classes fairly regularly and is a pro at doing these kinds of things. He's going to do a bit of a lecture, and then there's going to be a set of labs to actually play on a real Docker cluster and actually play with some of the stuff we'll be talking about today. We are recording this though, so if you have a question, please put your hand up. I will bring you the mic. Please ask all your questions on the mic. Otherwise, we don't get it on the video. I would ask Phil, otherwise, if we don't get the mic there in time, please repeat the question. But otherwise, off you go to Phil.
All right, great. So thanks everybody for coming. Maybe I'll start with kind of setting expectation of what I'll try and cover. First of all, let me talk about the material briefly. I think there may even be a slide on this. So this material has been written by a set of instructors, starting with Jerome Petazzoni, who is no longer at Docker, but was one of the very early employees at Docker, and who did tons and tons of training for Docker, introducing people to Docker, talking at conferences. So he created a massive, and I will reiterate, a massive amount of material about every aspect of Docker, which now includes a full Kubernetes workshop. And so this is all open source. You can go, so on this first slide, I think I had the link there. Container.training is a collaborative, actually that then links you to the actual GitHub location, but container.training will show you all the ways this workshop is being used, the next few conferences it's going to be used at. By going to this URL, you won't find the slides I'm showing you today, so it's customizable. I can go in there and turn on and turn off chapters. And so what I've done is I've tried to cut down hundreds and hundreds of slides off of this material. We still probably won't get through everything that I have up here today, but a lot of slides will have a little magnifying glass in the upper left, and that's kind of the deeper level of information. And so because all this is accessible to you, and then I've actually uploaded the PDF and the HTML to this, to today's session, to both the C-ALE GitHub site, which we can show you the URL for that, and I will also upload it to the OSS Summit Vancouver website. All that to say, whatever we don't cover here, all this is very interactive. All of the Play with Docker site is always available. So whatever we don't get through here, you'll have opportunity to go through this at your own pace in the future. So hopefully that'll be helpful. I also will try to keep the pure kind of lecture content to a minimum. How many have heard kind of an intro to containers talk somewhere in the past few years? All right, so maybe half. So yeah, I won't do the deepest dive. There was also the LXC folks in here this morning. Again, all that information is available. We can even do a little interactive if there are questions about particular aspects of that you want to talk about, we can do that. So yeah, I work for IBM Cloud. We have a container offering like many other clouds do, so that's why I happen to work on open source, whether it's Docker, Containerd, and like the introduction, I've both given this workshop and given a lot of talks about Docker and the container ecosystem. So let's dive in and see how much we can get through. Again, there's other places to find lots of information about Docker. Here's the actual GitHub location for Jerome's container.training. Again, you can customize this material, and what you're seeing today is a subset of everything that's out there. And again, yeah, if you actually load this up as HTML, there's some nice features where you can actually go to GitHub for this particular slide, and if you have a change or a submission, you can do that. I mentioned the magnifying glass slides. These are all the chapters we're going to try and talk about, a little bit about the history of containers. We're going to interleave this actually, so rather than do 45 pure minutes of talking and 45 pure minutes of demoing, you'll see this our first containers back. That will actually type in commands to either play with Docker or your own Docker setup. So that'll be our first chapter. Then we'll talk about Docker images, what that means to create an image, how we do that with the Dockerfile. Again, we'll do this interactively. I'll explain something and then we'll try it. A little more about images. Again, if we run out of, if things are moving slowly, we may have to skip some of this because these are more advanced topics. And then when we have containers running, how do we give them names? How do we look at what they're doing? How do we look inside a container? A little bit about networking and volumes, again, if we can get there. And then actually this isn't the last, but this is more, these are topics that if you came to the LXC talk, again, these are features of the Linux kernel that are used by both Docker and other container runtimes or engines. So again, you may have gone that elsewhere. We'll see how we're doing when we get to that point. And we'll actually talk about the ecosystem. Docker is not the only way to run containers, and we'll look at that a little bit. And again, I'm happy to be interrupted at any point, so don't worry about raising a hand or asking a question anywhere through here. This is, again, Jerome's content for Intro to Docker. I'll probably jump around a little bit just to give my flavor of that. But this is effectively, I'm going to move here. My clicker doesn't want to talk to my thing unless I'm standing this way. So again, containers have had a bit of an evolution or a craze in the past few years. Docker, the company was part of that. But a lot of the features that containers offered have been around in the Linux kernel for decades in some cases. The concept of namespaces or control groups. And so they're offering a set of solutions to a set of problems that have existed in the software industry for a long time. And we've always tried to find ways to make this more efficient. So, at one time we installed our, assuming Unix or Linux, we took a physical machine, we installed the operating system, we installed a bunch of dependencies for an application that we wanted to run, and then we installed maybe a database on a different physical machine, and we maintained these machines. And if there was a hardware failure, we'd have to figure out how to migrate our application somewhere else. And then we found, virtualization could allow us to install multiple applications on the same piece of hardware, and each operating system instance had isolation from the other. And then as people had the ideas of more microservice-based software, containers were kind of this natural fit of an even more lighter weight packaging around an application or just a piece of an application that provided a service. So, moving away from monolithic to decoupled services and being able to iterate very quickly on that. So we'll see when we build an image that we can build a container image in a few seconds. And we're not building a gigabyte size operating system image or even a 300 megabyte operating system image. And we're not booting that image. When we run a container, it's like the same speed as running a process on a Linux or Unix system. So again, the containers aren't necessarily a brand new capability. A lot of these isolation characteristics have existed for a while. But Docker and Docker's version of that came at a time when a lot of people were trying to solve this challenge, and it just so happened to fit and become popular for that reason. Again, this is a longer version of that again, as you thought about trying to put an application on the same operating system with other pieces of an application, you're now figuring out how to get different runtimes. So Python and my JVM and my database, and trying to work that through a whole development to production cycle was complicated. And so again, trying to deploy all these different pieces onto different pieces of your infrastructure can be complex, and in many ways has been complex, and containers were part of that solution. Again, part of the solution being I don't have to worry about whether that department's application used a different version of Python and depended on different modules than mine did, creating possibly conflicts in production over, well, my application needs this version of the JVM, but yet we have to keep this version around for this other piece of the application. With containers, all those dependencies could be packaged and isolated from anyone else's application piece. And so you may have heard people talk about this parallel with the shipping industry, that the actual physical container, in fact, if you look here in the Vancouver Bay, you can see the container ships and the container port. That was really a huge improvement on the shipping industry of trying to find a standardized way to get products and goods from one place to another using common tools. And so they solved that with this creation of this standardized container. Everything goes in there, every tool in the system, every train car, every ship knows how to deal with that steel box. And so again, that concept has been used to where it solved that challenge for the shipping industry. We've seen that in many ways containers have solved that. In the software industry, where we package each part of that in a container, and as long as we have that engine in our systems that need to run those containers, then we can do that in a consistent way across all these platforms and through our pipeline all the way from a developer's laptop to a production system. So again, solving that matrix problem of dependencies and pieces of applications. Again, if you have gone to other large conferences or gone to DockerCon, you have very large customers talking about how containers have solved various time, money, or cost issues by moving from either a bare metal or virtualization model to containers. So again, there's a lot more information that you can find there. Another way to think about it, so that's kind of why containers are interesting from maybe more the business challenge side. Just thinking about how you as a software developer might try to explain to an operator how to install your application. And maybe you could write down the instructions in a text file, or you could actually write a script that installs those pieces on the type of distribution that you're used to working with or that your company wants you to use. And again, containers bring that all into a Dockerfile. We'll understand how a Dockerfile works to organize the laying down of the right dependencies and your software components. And you can build that, and if it builds on your machine, it will build anywhere. Again, because Docker has standardized that component. Another great demo that's been shown, many times has been shown at DockerCon, is the ability that if the software for your company is packaged as Dockerfiles and images have been produced from that, having a developer come in on day one, instead of spending half the day or a whole day or multiple days trying to install all the right tools and all the right pieces, that developer can instantly use these images. They can clone the repository. They can use a tool like Docker Compose and bring up all those pieces and be immediately productive, with development environments or even integration QA environments. Again, Docker has been very useful in CI, continuous integration systems. So again, everyone's using the same tools on the laptop. That can be tested in a QA environment as well. You get no pollution when we're using containers because every container instance is a new runtime. And then obviously using images as build artifacts, so actually packaging your software in a container. Now I can label each container with a version. I can do rollback. And again, many more complex higher layers above Docker are now obviously providing these features, whether we're talking about Docker Swarm as an orchestrator or Kubernetes can do some of these features with a lot of very interesting capabilities, like testing on rollout and doing auto rollback if there are errors deploying the new version of your software. Yeah, so again, taking a monolith and decomposing it, now we can also talk about how containers can be, can use like a service mesh or service network to actually connect to various parts of your application by name. So again, allowing us to decouple that. So our code isn't hard coding the IP address of the database server, and so now if I move that somewhere else, I've got this problem of trying to update applications for different infrastructure. Yeah, so like I said, many of the pieces that Docker is built from have existed for quite a long time. What changed with Docker was providing this Docker image format, which is now an OCI standard. If you've heard of the Open Container Initiative, there's an image specification that Docker and everyone else who's interacting with container images uses. A lot of the features in Linux that as I mentioned, existed before Docker were either difficult to use or complicated to understand all the components. So Docker's mission was, I want people to understand if they run Docker run and a container name, all the right things happen under the covers, and you have a running container with the Debian image. And so again, a lot of what Docker brought to the table was this ease of use for developers. It caught developers' attention because of the simplicity of the user experience. And so a lot of that has been brought by Docker showing up on the scene. Yes, we talked about the format, and again, the OCI came along. I think there's some slides about that. Bringing standardization and portability, making it easy to use, and providing reusable components around that. Again, you know, pre and post Docker, a lot of other formats have been used. A lot of those same challenges are in those environments. And so again, Docker brought this idea of a container image. All the dependencies are there. We'll talk a little bit about the layer format of images and how that actually saves disk, network, and memory usage as well when we ship things as layered container images. This is an example, and again, when we get hands-on, this may be a little more clear. But as we build up a container image, we start with some kind of base. In this case, you could start with CentOS, for example. You could add the JRE. You could add the Tomcat binaries, any dependencies of your application, some kind of plugin that your application needs, then your jar file, and then some kind of configuration. So this set of steps would happen in that Docker file. When you build it, all these layers would be combined, and your application is now a portable, shippable container image. Looking at it, so I've talked mostly to developers, you know, ease of use, packaging, and containers. Again, ops has always struggled with this concept of, you know, works on my machine. The developer says, I have these things installed, same as production, I have the right versions. Obviously, there can be drift when we're talking about, you know, mutable infrastructure where an operator can go in and update a package or install a new dependency. And obviously, all of that causes some friction. Docker brought the idea, now ops has to worry about, okay, development says this container image is ready, here's the version, and you know, the tooling for both dev and prod then become aligned, and that we're both running the same container image, which has all the same dependencies and components, and so that limits problems at the lower layer. Okay, maybe it's a container runtime bug or an operating system bug, but it takes away all those problems at the higher layers. So that's a very kind of fast introduction to how Docker came about, why it exists, what their goals were. There's a nice throwback to IBM VM. if we're talking about the history of containers, again, this is mostly to show, and these are links if you get the HTML copy, and you can actually follow through to the history of early work in container type isolation. Solaris and FreeBSD are usually noted as being kind of precursors to this idea of Linux containers. And Serge, who was just here and gave the LXC talk a few hours ago, he has a great blog post on this one topic as well. And again, I'm gonna skip through some of this. So again, we talked about that coming from the virtualization world to containers. PaaS was part of that. Platform as a service. Cloud Foundry said is tomorrow. There's going to be a talk in the. So yeah. So when Docker was created, it came out of a company, a startup called .cloud, and .cloud had created a platform as a service based around their own custom container engine. So Docker didn't exist at this point. They were using these capabilities of Linux. It was actually based on OpenBZ, and then they moved to LXC. And so it was actually originally written in Python, and later on became what we know as Docker. And so Docker was actually shown in March 2013 at PyCon. It was a very funny demo. Sullivan Hikes, the founder, actually mistyped the message that was scrolling on the screen. So I can't remember what it was supposed to be, hello Python or something like that, but there's a misspelling in it. It's like going by hundreds of times. So it was a lightning talk. He just had a few minutes to show this new idea. But it was at that time that they put it out in open source, and people kind of started to fall in love with this idea of this simple Docker interface to the container capabilities that existed. So many, this is actually kind of a positive story. So as I said, in the early days of some of these features in Linux, they were hard enough to use that there wasn't a huge user base, whether we're talking about LXC or OpenBZ or other usages of the namespaces and C groups in Linux. But as soon as Docker had thousands and tens of thousands of people trying it out and playing around with it, a lot of these bugs were fixed in the kernel. Many people who were here at this conference were involved in that, including the LexD team at Canonical. And so as a result of that, there's been a huge growth and stability of the container ecosystem in the last few years. In 2015, there was the 1.0 milestone. Actually, that was in 2014. Other tools started to add Docker support, like Cloud Foundry. The Open Container Initiative, as I mentioned, came around in 2015. Other engines came out, like CoreOS released Rocket around the same time. And also that same summer, the Cloud Native Computing Foundation, which is now the parent foundation over Kubernetes, and Containerd, which is a container runtime that Docker relies on, that I'm actually a maintainer of that project. We're part of the CNCF as well. So again, this period I think was very important in the sense that it wasn't just about Docker the company, but it was about the formats and some of those basic tools that they had provided being standardized into the OCI and CNCF. Again, Docker is much more than just a container runtime. So as I mentioned, there are other container runtimes out there, but over the years they've built a series of tools around that. And obviously Docker in more recent years has wrapped a lot of this up into an enterprise product that they sell for people who want to pay Docker for support for not just having a runtime, which you can get for free obviously, but for all the features around that. And obviously many other players in the container space have enterprise capabilities as well. So with that, good. So that only took me 23 minutes to get kind of a lot of the background out of the way. Before we move on and start to jump into some practical, let's let's use Docker, let's try out what it means to run a container to build an image. Any questions about that first bit of material? Wow, it was perfectly presented, no questions. Good. All right, so we will move on then. I talked about 10 minutes before we started about play with Docker. I don't know who, maybe there are a few people joined the room since then. So let's see, I have the URL up here for anyone that did not, although it's very small. Workshop.play-with-docker.com. Yes?
Sorry, is everything we're doing here today with the open source part of Docker?
Yes, yeah, there's no enterprise edition.
No enterprise
In fact, this session is really meant to be a Docker 101, so we're not going to get past just basic features that are available in the open source engine. Yep.
I just want to reiterate, in fact, all materials you see in ALE are CC by SA and GPL and or MIT. So essentially all of the only things that can be shown in these sessions are in fact free, as will the videos also be available.
Yeah, so the URL is workshop.play-with-docker.com. And that'll be useful to anyone who wants to actually follow along and type the commands that we're going to be showing on the screen. Once you get to that, you should get a page like this. If you click the Start button, you would come to a page that doesn't have this black box here yet. You would have to click Add New Instance up here on the screen. That will start what's essentially a VM on a cloud provider and show you a console here on the right. So you're at a command line. You can type Docker version. You can see that the Community Edition 18.03 is installed there. If you would rather interact with the terminal via SSH, there's kind of a nice feature here. There's a SSH and a URL, and there's even a copy button there. So if you copy that SSH command to a terminal on your system, you can actually log in via your terminal and not have to deal with this web-based client. I may actually do that because anything I type here is probably not going to be visible, and I don't think I can change that font. So let me do that while I'm thinking about it. Yeah, that's interesting. I wonder.
Didn't resolve for me either.
Yeah, I forgot to test that before we started. Oh. Yeah, I forgot to test that feature when he set this up last night. If we have a short break in a minute, I'll send him an email and see if he can fix the DNS. But for now, that leaves us with just this window for the moment, which isn't the end of the world. Also, if you don't like editing files at the command line, there's a nice feature here. There's a small button that says Editor. That will open a new window. And you can do very simple things like create a file. Say you have an editor you like on your laptop. You can create a file and click the upload button here. And actually, once it's here, there's a simple on-screen editor. So if we upload a Docker file, you can type in here if you don't like to use VI or whatever is available in this on this VM instance here. So that's just a few basics about the environment. As I said, on this system here, I do have Docker for Mac installed, which means I can go to my command line and type Docker commands. So if you have that, that's another option for interact. We're not going to be doing a lot of heavy interaction with huge images, or so the Wi-Fi should be capable for that. Any questions before I move on here? Because I want to make sure anybody that wants to do the hands-on part has what they need to be be able to accomplish it. So we're good there? All right. All right, so play with Docker, we're going to use that. Obviously, if you have Docker installed. If you want to go through this material at your own pace, or you want to go to the container.training URL and look at the full course material, which has many more advanced topics, you can also use Play with Docker for that. And again, you have 4 hours every time you log in to do whatever you want with that environment. So that's another option if we don't get through much here. This probably makes sense just to, again, give people a basis of understanding if you haven't done much with Docker. When we say install Docker, really what we're installing are two pieces. There's an engine and a client. The Docker engine is a daemon that runs on Linux, like many other Linux daemons. So that service has a Unix socket that it's listening on. You can also turn on TCP endpoints. And so this daemon manages containers the same way as like libvirt or some other hypervisor manager can listen and help you deal with VMs. The Docker client is how we actually talk to that engine. So when we type Docker commands, it's actually talking to that Unix socket and sending the command like create a container, start a container, build a Dockerfile. And again, the engine and client talk over this API, but that also means that many other people have written programs or client libraries that also can talk to the Docker API, which is not something we'll have time to talk about, but obviously if you're interested in that, there's a lot more resources on the Docker API as well. It's fully documented on the docs.docker.com. Yeah, so generally at workshops, can be complications with Wi-Fi, and that's, again, why we're using Play with Docker. Also, it can be complicated if you have a system on which Docker doesn't want to run, or an older kernel. So again, Play with Docker kind of resolves us having to do that. So if everyone's opened an instance on Play with Docker, obviously you can type Docker version and check. I think we're all on this 1803 level. So again, you should see something like this output here, 18.03.1-CE, and that's just a recent version of Docker. Although 18.06, the versioning these days is based around the year, so it's 2018. Month 3 was March, so every 3 months usually there's a stable release of the Docker engine. So 1803 was the March, 1806 is the June version, but there's no features or special things we need from the most recent version, so this will be fully capable for what we want to do. So let's talk about an actual container that we can run. So at the end of this section, hopefully you'll actually see Docker run a container. So in your environment, you should be able to run this command, Docker run Busybox, and then echo hello world or any message you want at the end of that. And obviously, you should see hello world come out, but you may actually see, if this is the first time you run it, Docker is going to talk to a container registry called DockerHub and actually pull the image named Busybox to this VM where you're running the command. And so if I do that here, Docker run Busybox, echo hello summit Vancouver. So these few lines, is there a way for me to change this? Actually, I guess.
I think you can make it full screen by Alt-Enter.
Look at that. I just learned something new about Play with Docker. So let me make this even bigger. Nice. Screen. So obviously, if I run that, if I run any command using the Busybox image, I'm going to make that even bigger. Obviously, this time we didn't see that output, and that's because that image has then pulled to our local engine, and now it's cached locally. And so if we type the command Docker images, we'll see that I have a Busybox image with a certain ID, and its size is 1.16 megabytes. So again, we're going to talk more about Docker images, but that's obviously a simple example to show that the Docker needs the container image before it can actually run it. So you've run a container, and obviously it wasn't necessarily that exciting. We used one of the smallest images on DockerHub available called Busybox. Who's heard of Busybox before? Because it actually is unrelated to the container world. It's been something used in the definitely a lot in the embedded Linux world, but it's a simple. It can both be your init process as well as your has a whole suite of basic Linux commands. And so again, it's very, very small. And so we ran, when we did that Docker run Busybox, it downloaded that Busybox binary, which is packaged as a container, and it ran the echo command, which is implemented by Busybox, and echoed back the message. So again, very, very straightforward. In this case, let's run something a little more interesting. So we are going to run Ubuntu, and again, that's another image name, so it's going to have to pull it from DockerHub because your VM is brand new. So if you run Docker run and then -it space Ubuntu, after that download completes, you should end up at a prompt that is root at some random set of characters and then a prompt. Let me run that here. All right, so that took 20 seconds or so. So hopefully most people ended up with a prompt at this point. So it's running an Ubuntu image that is actually packaged and published to DockerHub, and it's updated. So because we didn't specify any tag after the Ubuntu name, which we'll learn about tags and labels, it's pulled what's called the latest. So it automatically appended the latest tag, and we actually can see that if I exit out of here and do Docker images. You can see that both for Busybox and Ubuntu, it's automatically used what's called the latest tag, which is a pointer probably to something, I don't know if Ubuntu image, we can look in a minute, but it used to be using 16.04, maybe it's been updated, the latest is pointing to 18.04, the Ubuntu version. So that's been pulled from DockerHub because we didn't specify it, automatically got the latest. It is a somewhat minimal installation of Ubuntu, and so we can look in a minute at the package count, but -it is shorthand for two flags to Docker run. I tells us that we want to connect standard info, which means we can actually interact, so our command line is useful. And -t tells Docker we want a terminal, so we actually want the ability to have that higher level interaction to actually do terminal commands so that the output looks correct for doing an interactive session. So let me go back here and run that again, and that means I can type ls here, and I can list this Ubuntu. I can do dpackage query. What's a command? I can see that the package core utils knows the ls file. So again, it feels like an Ubuntu system. Many of the commands are there. If you look in bin, this is a fairly standard Ubuntu system, and we're running it as a container, which means when I exit out of this, I don't know what distros used for these VMs. It looks like it is Ubuntu. Actually, it's Alpine.
LSB is
Yeah, I don't know if that's installed.
Let's see LSB dash release.
Oh, right, yes.
LSP minus release.
I guess, does Alpine not do the LSP? Anyway, it looks like it's Alpine. OS release is Alpine 3.7. So again, we were running a container that was Ubuntu, but the VM itself is running Alpine. So again, that's some of the isolation characteristics of Docker. Our container doesn't have to match the operating system in any way, allowing us to run anything in a container, including something like Busybox, or even less. We could put a statically compiled binary in a container and run that with no distro components at all. All right, so if you're still at your prompt, if you're not, you can do the docker run-it Ubuntu again. This is just showing that we can actually modify this container, so if you try and run Figlet, nothing happens because it's not installed. You can do apt-get update, and that'll obviously, if you work with Ubuntu, that will update your package cache, and then apt-get install Figlet. That should actually install Figlet in your container. Do it here. All right, so I have Figlet working here. Now that we're actually back in this container, where we are in Ubuntu, so I said I wasn't sure what latest tag was pointing to. You can see here that it is Ubuntu 18.04.1 is what the Ubuntu official image on DockerHub is using. All right, so we've installed Figlet. I typed hello, you can do that. Obviously, Figlet works inside the container. It'll be interesting to see if this still matches now that we're on 18.04, because I assume these slides were created when it was still on 16.04. So you can run this command dpackage-l and then word count how many lines to see how many packages. There's only 95 now, so there's quite a bit fewer packages. I guess the official image of Ubuntu 18.04 is actually slimmer than the historic Ubuntu that was on DockerHub. Any questions up to this point? Everything working for everyone who's following along? Makes sense? Command's working. Again, you can exit out of this container. And the interesting part here is obviously to show the isolation that everything we did in the container has no relationship with the host. So if I exit out, if this is really running Alpine, I assume dpackage won't do anything. Yeah, right, this is an Alpine host, so we can't even run dpackage, and obviously Figlet is not installed. Again, just trying to bring home the fact that our container environment is a totally separate environment from the host that we're running Docker on. Oh, yeah. Yeah, I mean, so the environment is, the Play with Docker environment is customized and managed by some administrators, so I'm sure that they've hopefully made the host as useless as possible so that people don't use Play with Docker for mining Bitcoin or well, who knows what else you might try and do with it. All right, so kind of summarizing, we ran an Ubuntu container. It was different than our host operating system. Obviously, everything there is independent. Even if we were running Ubuntu 18.04 host and an Ubuntu 18.04 container, there's no relationship between those two. There's an exception here. Windows containers cannot run on Linux machines, at least not yet, unless you use some kind of virtualization in there. So I haven't said it yet, but it's important to know that Microsoft has been very involved in the Docker ecosystem. And there is a whole version of Docker for the Windows, not just virtualized on Windows, an actual implementation of containerization in the Windows kernel. And they have two aspects of it. LCOW, Linux containers on Windows, so they actually do have some hypervisor magic to run Linux containers on the Windows kernel. And then, of course, they have WCOW, Windows containers on Windows. So they have similar isolation. Obviously, there's no Linux kernel on Windows, so they've created similar functionality. So that's just an interesting point. Here goes a mic.
Currently, when I go back into the operating system after I've exited out and come back in, the applications that I've installed are no longer there. Is that the normal behavior, or is that something specific to the
Yeah, and I think that's the next. Where's our container is, that's a perfect segue. So the container we ran, so say you only ran one, I ran a couple, it's now in a stop state, like Docker didn't destroy it yet, but there's no processes running. So that shell process we ran to be at that prompt, that shell process has exited, but we could get back to that container, but when we type Docker run Ubuntu again, that has no connection to the container we ran, so Docker spins up another one. So yeah, this is exactly what you experienced. If we start another container, we run Figlet, it's not there. We started a brand new container. Obviously, we could build an image that had Figlet installed, and then when we ran that container, it would always be there. But yeah, we'll talk about background containers now, but just to follow through on that point. So containers that we want to be longer lived, we can actually give them names. And I think actually let's go forward with this section, because I believe in this section we'll exec into a container that's already running. So yeah, we were playing around with containers interactively. We were sitting in a prompt and actually interacting with it that way. Most of the use of containers is actually not interactive. We create a container to run a part of our application, and we start it in the background, and we interact with it with other tooling. We look at the logs of it, we list and we find its status, we stop it, we start it, and so that's what we'll look at here. Let me just time check. So we're about halfway in. I think we're doing okay at this point. So if you want to run this, looks like Jerome has created a container in his namespace on DockerHub. So JPETAZZO, jpetazzo/clock. And if you run that, it looks like the goal of that container is just to output the time every second. Until you Control-C and stop it, it's just going to keep doing that forever. Obviously, Docker will need to download that image. And this is not part of Docker's official image set. So the first two we ran, Busybox and Ubuntu, we didn't prefix that container name with anything. So when we talked to DockerHub, those images were pulled from the official library. There's someone who, there's actually a team of people who maintain those images. When, for example, Ubuntu releases a CVE, those container images are updated regularly. But this is Jerome's image. We don't know how he created it. We don't know what it is, but when we run it, obviously he created something that just outputs this counting clock. Now, this time we're going to actually run his image again, but we're going to run it in the background. And all you should see when we do that is a very long hexadecimal identifier, and that's the ID that Docker gave to this instance of the container. And you won't see the clock output, again, because you've started this container in the background. So let me do that here, because I think we'll be doing, so we need that -D flag that runs it in the background. Right, so downloaded it, and then the very last line is this container identifier that I just talked about. So how do we know that's actually running? How do we know what's going on? One of the most common tools that people use with Docker is the Docker PS command, which is named that way because it has similarities to the PS command on Linux. When we run Docker PS, we should see, again, I've made this output large, so it's not quite aligned properly, but here's our part of our ID, the image name, the command that's running, which is, again, trimmed so it doesn't take up the whole screen. He's running some kind of while loop in a shell, and that's probably his clock counter. It's been running for 28 seconds or so. And Docker will give the container a default name if you don't provide one. And we'll look at how those are created here in the material in a second. So yeah, we see the truncated ID, the image, the command, and all of that. So let's start 2 more of these. And you do get tab completion, so once you have images downloaded, you can just type a few characters and tab, and because we only have a few images, it'll start up a few more of the clock image. So now when we do Docker PS, we should see different IDs, all running the same image, all running the same command, obviously up for slightly different amounts of time. And again, you should see all that when you run Docker PS. There are many, many flags to Docker PS, a lot of very interesting capabilities. One of those is -l, just to show the last one. And again, you can see that for me. That would be somehow when the network gets a little poor, the interaction with the terminal gets kind of funky. All right, so that's the last one I started, this morning 7. You can also do other things like quiet, and that'll just show those IDs, and so that allows you could then automate other commands. Say you wanted to stop all the currently running containers, you could do Docker PS-Q and pipe that to another command that then killed or stopped all the containers that come back from that. So that's a very useful flag. And again, you could do start combining flags like LNQ, show me the last, and just show me the ID. So again, because these are in the background, we don't see the output in our terminal. Of course, that's what we want. We want them to be in the background. And so the way that we can then look at the output is to use Docker logs. And so you can notice that you can type just enough of the ID to make it unique. So maybe just a few letters or numbers. And unless there's a conflict and there's many containers using that, it'll automatically match to the correct ID. And so for me, if I look at the very last run, Docker logs 1E7, again, I get the output coming from his clock script in his image. So yeah, we only used a prefix of the full ID. You could specify the whole thing. That output everything that had been logged up till that point. So I saw every second since I started it. We can do things like tail. So Docker logs --tail 3 shows me, again, the last 3 lines of the log. You can also do dash, yes?
Is log size restricted?
So the Docker engine is configurable. It will actually do log file rotation and max size, I think. But I want to say by default, if you just install Docker and don't specify anything, it's unbounded, I believe. So you mean Docker storage of these logs? Yes, I believe unless you configure it, it's unbounded. But we could hop to the Docker documentation to verify that in a minute. Any other questions? So yeah, we can follow, which again is nice to be able to watch in real time. So you're following the output of something that you started in the background. Again, if you do tail end follow, you'll see one line of the previous output and then it'll follow until you control C. So again, you can try any combination of these yourself. Since we have containers running in the background, obviously we aren't interacting with them, so we can't exit, we can't type exit of the shell, we can't control C the process. And so there's two commands that can be used to terminate this background or detached container. The Docker kill and the Docker stop command. So again, if you know much about Linux signaling, you know that there's a kill signal, sig kill. So that's what Docker kill does, which won't allow your program to clean up in any way. Sig term is what Docker stop uses. It will actually send sig term to the process in your container. But if it doesn't respond to that after 10 seconds, it will actually send a sig kill. So again, these are two ways to stop that. You can pick one of your containers and stop them. In my case, I'll stop 1E7. And you'll see this is blocking, and it may be that that his shell script didn't have a handler for sig term, and so let's see if he talks about that. Yeah. So because his shell script doesn't have any handler for sig term, Docker waited 10 seconds and then sent the kill, and then terminated my container. So again, we can kill the other two. At this point, Docker PS, Docker kill, DC2 477. And now if we type Docker PS, we don't see any output at this point. But if we add the -A flag to Docker PS, we'll actually see all the containers we've run so far. So try that on your system.
Yeah.
Not even on.
There we go. Thank you.
I'm sorry. I hope I haven't been hard to hear in the back the whole time. Okay, let's start over. All right. So we've typed Docker PS-A and we see everything that we've run since we started this instance in our, if you're in Play with Docker. And we can see that they've all exited. So that's why the standard Docker PS command doesn't display them, because they're not actually running. But -A says any container in any state show me their information. And of course, if they've exited, it shows the actual return code. And we can see with the clock images, we actually have an error code because the kill was used. There wasn't a successful process exit. So again, it's a little cleaner to see on his slides because we're not, don't have that big font kind of rolling it over a couple lines. So yeah, this is kind of a section break, so maybe I'll stop here. Is there anything up till this point that people have a extra question on? And while people are thinking if they have a question, let me go to docs.docker.log file size. And that's too small. So the JSON file, there are many logging drivers in the Docker engine, which obviously we don't have time to go into that. But the default one is called JSON file. If you actually look at the file on the file system, say you're an administrator and you have control of a system running Docker, you can go actually find that place where all these containers are sending their output. And it's a JSON file that you could parse with a JSON interpreter. This is an example setting the max size to 10 meg. But it does say it defaults to unlimited, so it won't limit the log size. You can also do interesting things like actually have multiple files and do log rotation as well. Any other questions before we move on? All right. So yeah, we've run both foreground and background containers. Now we're going to look at attaching and restarting. Yeah, so Docker itself is not putting these containers in categories. That's more our perspective of whether they're sitting in the foreground or not. If you do start like a more traditional kind of distro container and you're sitting in it at a prompt using the -it, you can actually detach from it. This Control-P, Control-Q is the sequence to do it. But yeah, actually you could also kill so there's a client process that's actually handling the output from the container, and obviously killing that process would do the same thing. You can't do it by hitting Control-C because that is delivered through that API to the Docker engine and delivered to the container. We already talked about -T and -I in the prior section. There is a way to actually specify a different detach sequence if that's important to you. You can, in this case, change it to Control-XX. So we need a running container for this. So yeah, one way to do that would be to go back to, actually no, we want a background container. So if we have Ubuntu running in the background, which is effectively running a shell, that's the default command. So I did docker run -d Ubuntu. If we docker ps, well, actually we can't do that unless we have a TTY running, because the shell will just exit. There we go. So you can see the default command for Ubuntu is bin bash. So that bash won't run if it doesn't have a TTY to talk to. So when I did that without a TTY, it just immediately exited. So now we have Ubuntu running in the background. And so our docker attach command just needs a container ID. You could do it with this nice little, hey, show me the last container and just show me its ID, so the docker ps-lq, or you could actually just type the part of the container name, so EAB, and you can see that we're at our prompt, but we didn't connect standard in, and so what is the attach? Oh, so I made two mistakes. So first time I didn't have a TTY on my background container, but I also didn't tell it there'd be standard input. So even though I can attach to it, you can see that this input is not actually getting to the container because I'm not getting another prompt. And so let's stop, and I'm going to actually remove that. Let's try to do it the right way now. TID Ubuntu. So now it's in the background. It knows I'm actually going to want to provide standard input, and it has a TTY. And so now if I attach to it, I have a working prompt. I can list files there. I can do whatever command. So basically, I still now have a background container, but I can still go into interactive mode with it using Docker attach. So that's one method of basically connecting to a backgrounded container. Yeah, so obviously if I didn't start my container properly, then I couldn't attach to it or detach to it properly. Yeah, so the recommendation here is if we want to interact with a container by sending it input, Docker attach. If we have a background container and we just care about its output, obviously Docker logs makes more sense. So we had a bunch of stopped containers, and most of them I did not remove. If I exit out of that, because I was actually in the shell, I exited the shell, so I did just stop this container, but I can restart it. Let me just show the last one, so it's a little simpler. So here's the Ubuntu I just exited out of 17 seconds ago. Its ID is 7F1. So I can restart that just by typing docker start and that ID. And now my shell is running again. So in this case, if in this container I installed other tools, they would still be here because again, I haven't started a new container. I've restarted one that I'd already exited out of. This is a little bit deeper information. So if you have a container running a process that has some kind of TUI or interpreter where it's waiting on input, sometimes when you attach, it looks like it didn't work. But if you hit enter or some other input character, that usually triggers that interpreter or TUI to wake up and send you a command. There's been a lot of bugs open over the years in the Docker repository. People say, hey, Docker attach doesn't work because nothing happens. But if you hit enter, that starts the interaction. So yeah, there's a signal that gets sent on Docker attach. Again, because you're attaching maybe from a terminal that's different size or because of the fonts, this sig winch will actually send the rows and lines, and most interfaces will then start to work properly. All right, so that's most of like the real basic Docker 101, run, stop, kill, attach, logs. But we've been doing all of that with images that already existed. Someone else created them. They're already out there. Now we're going to look more at what it means to build a Docker image, our own image, and run it. So we'll talk about an image. We'll talk what is a layer, image namespaces, how to search or download images, image tags. And so hopefully that'll give you a good basis of knowledge for what it means when we're talking about a container image. So a Docker image, and as I said at the beginning, the Open Container Initiative has taken that format and standardized it. So even if we're talking about other runtimes that are OCI compliant, all these same things hold, whether we're talking about running an image with Docker or Containerd or Kubernetes or some other tool. Images are always made up of files and metadata about the image itself, things that we want to store. The files themselves, those will become the root file system. So when we do that Docker run Ubuntu, and we're at a prompt, it looks like we have a full file system here. That's because those files are inside this image along with some metadata about that image. The metadata has a lot of detail about potentially the author, what command should be executed when people start that image. Is there environment variables that should be set? and all kinds of things like that. Images are actually made of layers, and I think given the time, it's unlikely we'll talk a lot about union file systems, but Docker and many container runtimes use this layered image concept so that when you're actually running an image, those layers are combined in what's called a union file system. So each layer can add, change, or remove files or metadata from the lower layers. And the cool thing is, when we're running 10 versions of Jerome's clock image, we're not actually making copies of that file system 10 or 100 times. And so that's the what we mentioned earlier about optimizing disk usage, transfer times. We don't need to copy that image every time or use more memory to have that same base image underneath our containers. Again, we looked at this early on as an example, so we're coming back to this Java web app that Jerome has as an example. So when we run this container, we don't see this happening. Actually, you might have seen this when you typed Docker run Ubuntu for the first time. You saw that pull from the Docker registry show a bunch of IDs and sizes as it downloaded each layer of the image, because when it talked to the image registry said, hey, I have 10 layers. Here are the IDs of each one, and here are their sizes. And then the Docker engine downloaded each of those and then combined them. So this is, again, a conceptualization of this union file system concept, that all the downloaded layers, in this case, he's talking about an Ubuntu 15.04 image. It has this large kind of base layer and then these very small. We can assume those are probably metadata because they contain very little content or maybe very small files. And then the 0-byte layer is just pure metadata. There are no files in this layer. When we actually Docker run that image, Docker then adds this thin read-write layer above that when it stacks this file system, so that we can install a tool like Figlet. That doesn't touch any of these layers. That was installed in this temporary read-write layer on top. So when we started a new container from Ubuntu, we didn't see Figlet because that layer was only associated with that one exited container. And so again, that's probably as much as we have time to go into that concept. Again, each running container gets its own thin read-write layer. And so every container that's running has the read-only set of all the layers of the image, and then this read-write copy of that upper file system. And so there are many file systems that support this in Linux. Docker actually supports quite a few of them. So AUFS has been for many years the default, but was only supported by Ubuntu. OverlayFS has much broader support and is more likely the default these days. Supported across many distros, ZFS, ButterFS. So again, these are file systems that support this stacking copy on write mechanism. So yeah, you could compare this to object-oriented in a way. Containers being an instance. If an image is a class, containers are actually an instance of that class, and that there's inheritance involved with the layers and their parentage. So right, if we're talking about running an image, there's no way for us to change that image. There's only ways for us to add or change information at this read-write layer. You can then take that and create from that a new image by changing, removing, adding things, and that's effectively what we do when we build images. So right, effectively, every container has to start somewhere, and so there's a special empty image called Scratch, and that's one way to start a container with absolutely nothing in it, is we can write a Docker file that says from scratch and then just start building up content from the ground up. We can also take tarballs of file systems and use Docker import to become a standalone image. Most people won't be doing that, but if you can think of how a distribution provider might want to start providing an image for Docker, they could create their sort of pristine copy of Ubuntu 18.04 as a tar file and then import that, or do a from scratch build and copy in all those files as a starting point. There are ways to actually do this interactively. So Docker commit is a way to say, hey, I've made changes to this container's file system. I now want to save that as an image. And so you can use Docker commit for that. And it's an interesting way to kind of learn how layers work. But Docker build is a much more popular tool that actually does a similar thing to what Docker commit does. It runs every step of your Docker file as a container and then commits that. And that allows you to have this repeatable build. Before we do build an image, when we're talking about DockerHub, which is the most common place, when the Docker engine sees that you've asked to run or pull an image, it automatically defaults to talking to DockerHub. And in that case, if there's no namespace specified, a user or organization, then it's automatically going to look in the official image repository for that image. So when we ran Ubuntu or Busybox, that's what it did. Obviously, users can have images in their own namespace, so other people, you can share them with others, you can make them private. Obviously, other people can't write to your own registry. That's controlled by your own authentication. But then you can run your own registry. So many enterprises who use containers don't want their developers or even their production systems to be using an image from DockerHub that may not meet some standards of the company or be scanned by their tools. And so many companies obviously set up their own registries internally that then you can specify on the command line, docker run registry.example.com / some images. And many other public cloud providers also have registries you can use. Google Cloud has a registry, Amazon has a registry, IBM Cloud has a registry, Azure has a registry, and there are even other providers. So again, that's kind of understanding how image references work. Yeah, we won't talk through this, but again, if you don't specify a namespace, that's where the Docker official images are hosted. They're maintained. They're not just put out there and left. They're actually maintained on a regular basis. Your own namespace is, again, based on your DockerHub user ID. And then running your own registry allows you to use DNS or any specific port that you'd like to listen on and the name of an image or however you want to categorize your images in your registry. So yeah, you can use the Docker client. So far all we've done is we've seen image pulls by running them, but you can also use the Docker client to push an image to a registry. We already typed the Docker images command, and it's pretty unimpressive at this point because we've only run 3 of them. We have Ubuntu, Busybox, and Jerome's clock image, but that obviously is a useful tool to both see the size of an image, information about its ID, when it was created. And there's actually a simple search capability to actually look for an image on DockerHub. Say you're looking to see who has created a packaging of maybe a popular open source tool that you'd like to use. You can look on DockerHub for that. So all we've done so far is use Docker run to automatically get an image pulled. But you can actually use the Docker pull command to simply do that pull operation separately from then running it. So if you know the name of an image, you can Docker pull before you do Docker run and bring it to the engine. So in this case, you can try this Docker pull Debian : Jesse. So this is the first time we've talked about the second part of an image name, the tag. In this case, I'm not sure what the default is for Debian. But Debian : Jesse pulls the Jesse named release of Debian, and obviously there are other Debian releases out there. One thing that we're running a little short on time, but you can always go to hub.docker.com, and I guess it defaulted to my own repository. But there's also search here as well. And why was I going to show you that? Oh, I was going to show you that this is somehow searching only my repositories. If I look at the, what I wanted to show you is that the official Debian image, every official image has a great page like this that tells you all the tags that are supported. So obviously there's Buster, experimental, Jesse, old, stable, all kinds of SID, stretch. So this is a little more useful on the web if you want to go look at Ubuntu and say what tags are available. And the great thing is you can actually see exactly how this particular image was built by clicking on the Dockerfile link. And you can see it's actually quite simple. It's from scratch. It adds a tarball, which is, I'm sure, Debian Buster, and sets the command to bash. So that's obviously a very, very simple image. So yeah, we talked a little about tag. Latest is always updated to, again, when I'm talking about the official images, that gets updated to point to the latest stable supported image. Obviously, tags are useful when we're actually talking about how we're going to version our software, how we're going to make sure that this software is going to production. We want some way to identify which version is running. Obviously, if we're just doing development and playing around, it's okay to not really specify tags. So that's a whirlwind tour of images. Since we only have 10 minutes left, I'd like to at least get us through writing a Dockerfile. So a Dockerfile, again, we just saw a very, very simple one that from scratch, adding a tarball, setting the command. They can be simple, they can be quite complex, but effectively once we have a Dockerfile, we can use the docker build command to actually execute that and to create a named container image. All right, so yes, we do want to create a directory. So I'm going to make dir my image and go into that and edit a Docker file. So if you want to, definitely follow along. So I'm in an editor. You can also use that other feature, the Docker Playground, if you want to create this in your own local system and then upload it. And here's the 3 commands we're going to put in this Docker file. From Ubuntu, run apt-get update, run apt-get install figlet. So I'll type that here. From Ubuntu, run apt-get update, run apt-get install figlet. So I've written that. If I cat it out, it's just those 3 simple lines. So we're actually going to build this with this command, docker build -t figlet, and then dot is specifying that the directory I'm in is the source where to find the Docker file or the source of any files that are going to be part of copy commands. And T is the tag to apply to the image, so that will actually be our image name. So I'm going to do, let me get this, docker build figlet dot. Now here, it scrolled pretty fast, but it did the from Ubuntu, and then you saw the first run command, and now it actually installed figlet. And at the very last line, it should say successfully tagged figlet : latest. And so that means if we type Docker images now, we have a new image called Figlet, created 13 seconds ago, and its total size, which is the Ubuntu plus the new packages that got installed. Again, he shows a simpler version of this, kind of cutting out a lot of those run command output. You'll see these steps as the output of Docker build, showing that it's following your Dockerfile step by step. I'm going to try and breeze through here so that we can get to a stopping point. Yeah, there's a lot of useful things to learn here that are a little more advanced about how Docker build works. So it's caching each execution. So if we don't change that Docker file, if I run it again, got to type slower. Build -t figlet dot. Oh. You'll see that it happened much faster for one, but you'll see here using cache. And so because nothing changed in the Docker file, the Docker engine already said, I've already built that before, and I know that this image, this layer ID, this container that ran already has the output of that. And so there's a lot of useful capabilities about Docker build's caching system. But now let's run it to verify that now if we look at Figlet hello, you'll see that we didn't have to install Figlet in this image. We didn't have to do the apt-get update. Figlet is now installed in this container image that we've named simply Figlet. So again, very simple, just built a simple image, layered it on top of something that already existed, and added what we wanted. There's an interesting history command that will show you like the history of the total image. So again, there were parts that we had no part in, so that's the building of the Ubuntu image that we started with, and then our commands are here more recently in the history. I'm going to skip that for now. I just wanted to make sure we got to the end of that and talked very, very, very briefly about these two, command and endpoint. So in this case, he says, okay, our container runs bash by default, but it'd be cooler if it actually ran Figlet, so that when people run our container, it actually runs Figlet. And the way we do that is we can add cmd figlet-f script hello, which will actually output with the nice script font the word hello. You can put command anywhere in the Docker file. The last one wins. So if there are multiple CMD entries, obviously that means there's no interest in doing that. Again, if you add this line to your Docker file, if you have a second to do that and rebuild it, you'll see that, it uses cache for the first three and only adds that command. Now we would actually have to override the default command by typing bash if we want to do an interactive container. But if we just run Figlet by itself after doing that build, it'll actually output hello. Entry point is interesting because it allows us to say Figlet is the entry point, but anything after that will be flags or extra command content. And so there's actually a great blog post if you want to learn more about the difference between command and entry point. In this case, he changes CMD to entry point, which allows you to Docker run Figlet and some other string, and that's what actually will get output. And again, if you have a moment, you can try that together. So yeah, I wanted to at least get to some breaking point, and we only have a couple minutes, but there's a lot more material here that we didn't get a chance to, but I wanted to at least get through the basics of interacting with the Docker command line and then also building a simple image. So we got through that, which is good. Any last questions, interesting topics that I didn't have a chance to get to? Yes. Yeah, so if you go to this container training material and search on health check, there's a whole section on health checks. The Dockerfile has a command to actually specify a monitoring command, like something that checks that your web server is actually responding. He also has a great section on just general monitoring overall. Yeah, this workshop is set up to be 4 hours or 8 hours, so there's a lot of material here. Yes?
Second here.
So the run command creates a layer, right? So we could have combined apt-get update with install. Are there any best practices as to when to go for the new layer versus when not to?
Yes. And again, there's so much, so much detail. So if you load up this material and look at this section, reducing image size, it talks about having these as separate commands versus combining them into a single run command, which obviously if we install or remove things, it's better to do that all in one command so we don't end up with layers that have files which are then removed by an upper layer. So there's a lot of great information about better efficiency of Dockerfiles.
Yes, I wanted to ask if it was possible to use Docker build to build for a different target architecture.
Yes, and I've been very involved in that because I work for IBM and we have some other architectures. So we now have multi-architecture support in the Docker engine. There are people doing interesting things with QEMU to do cross-building. But normally, kind of the easiest way is to build an image on the target architecture, push it to DockerHub, and then I have a tool called manifest tool, and now there's a Docker manifest command in experimental, which is also an IBMer that took my code and contributed to Docker, where you can combine a bunch of different architectures manifests under a single name in the registry. And so if I type Docker run and an image name that's multi-arch, if it supports my platform, it'll only pull that image. So ARM, in fact, a lot of those official images are supported across sometimes 5 or 6 architectures. So yes, the short answer is yes. There's more details behind all that, but yep.
I'm afraid we're out of time.
Yep.
All right. Well, I'd like to thank Phil very much for his talk on Docker. It's the end of the 5th session we've done. We still have one more today, which is Kubernetes, and tomorrow again we have software-defined networking and Cloud Foundry. But otherwise, I'd like to give a round of applause for the great talk.